Large language models operate on probability, guessing the next logical word in a sequence. Enterprise business intelligence demands strict deterministic accuracy. When you force a probabilistic engine to execute deterministic tasks, the system tends to destabilize. Connecting generative AI directly to private corporate data introduces three distinct hazards. The AI can hallucinate non-existent data points, multi-step reasoning loops generate untrackable cloud billing, and without governance, the model may surface sensitive information to unauthorized users. This is the architectural diagram for a custom agentic GenBI platform. We engineered this layout to address those security and operational risks. What you see is a governed ecosystem. We replaced the open-ended text box of a consumer chatbot with programmatic guardrails. A standard conversational assistant is designed to synthesize an answer from its own internal training weights. An enterprise data agent is instructed to do the exact opposite. If an employee asks for quarterly sales figures, relying on the model's neural weights ensures failure. The AI does not actually know your company's numbers. It only knows what financial reports typically sound like. To counter this, we introduce a zero-trust semantic orchestrator. This component serves as a mandatory abstraction layer between the user's prompt and the corporate data. The user never communicates directly with the database or the AI model. They communicate with the orchestrator, which interprets, filters, and routes every query. This design shifts the responsibility for accuracy away from the raw intelligence of the language model and onto the structural constraints of the data pipeline. Securing enterprise data requires us to abandon the search for a perfect language model. We achieve accuracy by shifting operational control into a governed routing architecture. Many developers assume they can force language models to behave predictably by writing massive system prompts packed with specific instructions. This approach leads to prompt fragility. Every time the AI makes a mistake, developers bolt a new negative constraint onto the prompt. Eventually, you are left with a contradictory text block that the AI cannot follow. Large language models suffer from attention dilution. When you pass a 1,000-word rule set to an AI, it focuses on the first and last instructions while potentially overlooking the dozens of rules in the middle. Massive rule sets also incur a token tax. Forcing the AI to process an enormous prompt for every interaction increases latency and drives cloud billing up over time. Beyond cost, language models have an inherent drive to be helpful assistants, a behavior often called eager pleaser syndrome. If a user asks a specialized finance agent a marketing question, the model's drive to provide an answer can override its written constraints, leading it to invent data outside its domain. The remedy is to move beyond the universal system prompt and implement zero-code agent provisioning via a data-driven control plane. Relying on text instructions is a brittle patch for a structural flaw. Reliability requires decoupling the business logic from the system instructions. When a user nets a natural language query through the Blazor frontend, the execution pipeline activates. This is layer 2. Here, the semantic kernel C# SDK acts as the central orchestrator, functioning as the primary routing engine. Upon receiving the query, the orchestrator checks the agent registry database to determine which specialized domain agents are active and available. It uses a volatile memory store to pull the database schema definitions for these agents and dynamically converts them into a searchable vector index. The orchestrator compares the user's text against this in-memory vector database to identify the exact intent and the required data tables. Rather than generating an answer itself, the orchestrator assigns the task to a specific domain agent, routing the query precisely to sales, marketing, or finance. If the user asks a complex question spanning multiple departments, the orchestrator splits the prompt into individual requests, firing them off to specialized agents in parallel. A switchboard architecture within Layer 3 routes these tasks by complexity. Deep reasoning tasks are sent to the GPT-4o API, while strict SQL generation falls back to a local model like 5.4. The system injects domain-isolated rules into the selected agent just in time, ensuring the model's attention is focused on a single, clear task. By mapping human intent directly to data domains before the AI processes an answer, the orchestrator functions as a traffic controller for business logic. Even with perfect routing, we must guarantee that an agent is restricted at the network and identity levels from accessing data outside its approved scope. Layer 4 shows the mechanism for contextual lockdown.
We separate the AI reasoning engine from the enterprise database. We utilize Microsoft Entra ID to assign specific managed identities to each domain agent, locking them to a strict permissions profile. During the routing phase, the orchestrator intercepts the user's role-based persona. It validates their security clearance against the Entra ID claims before SQL execution. The agents are forbidden from writing SQL against raw transaction tables. We push the calculation logic down into the data layer itself. We build a semantic layer inside Azure Fabric, consisting of pre-calculated golden views. Supplying the AI with clean, flattened metrics reduces the likelihood of structural confusion. The agent uses native tool calling features to generate T-SQL scripts targeting these locked-down golden views. The AI model never possesses actual database credentials. It constructs a query string and passes it back to the execution tool, which handles the secure connection. If a user attempts to ask for information outside their clearance, the persona drop-down simulation intercepts the request and denies execution. By locking the AI out of unauthorized database schemas at the identity level, we address hallucinations and breaches through structural exclusion. The final operational challenge is enterprise FinOps. Multi-agent architectures generate complex API billing, and IT departments often lack visibility into these sprawling costs. As this chart demonstrates, standard proxy servers often omit granular token metadata during intermediate tool calling steps. This creates a telemetry black hole, where you can see the total cost but not the departmental attribution. Furthermore, capturing telemetry in multi-agent systems can trigger the async local value trap, where parallel agents accidentally overwrite each other's log data. Traditional application performance monitoring tools are built for linear requests. They struggle to track the multi-hop reasoning loops generated by an AI orchestrator. Accurate departmental chargebacks require a thread-safe interception mechanism that can identify every transaction within the execution pipeline. To solve this, we implemented the AI audit filter. This component acts as a mandatory gateway between the application and the model endpoints. This deep scraper uses a recursive search to identify token counts and execution times across every reasoning hop the semantic kernel makes. Once it captures that data, the filter binds the token metrics to the user's identity and the specific T-SQL string that the agent generated. As shown at the base of the diagram, this telemetry is stored in the persistent audit log database, creating an auditable source of truth for AI-generated cloud costs. This database also serves a secondary purpose. By logging the user's intent alongside successful SQL execution, the system builds a golden query dataset used to train smaller, more efficient local models. Implementing this interception layer provides total IT observability. Administrators can issue accurate internal chargebacks by department. By integrating semantic routing, data governance, and FinOps telemetry, we create an environment where the risks of generative AI are managed through a verifiable architecture.